Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture. In the last class, we looked at the stress field near the crack tip, and I would like to continue in this class to look at the displacement field in the mode 1 uh, derivation. So we'll first look at the plane stress, what is given by the Westergaard stress field. So this is already established. This is a Westergaard stress field for the biaxial loading in terms of Westergaard Z function. I mean, stress function Z, it's called Westergaard function. So this we have already known, and then this is the uh, stress field, and this is the stress function, which is already we have seen. So in order to find the displacement field, we will use the stress-strain relationship for the plane stress case, and which also we know this from the theory of elasticity. We have already seen this. So we use this relation and then try to get the displacement field for the mode 1 crack problem. And for a plane stress, substituting the stress components in the above equation, one gets this as dou u by dou x is epsilon xx. This is from the strength of materials notation. So epsilon xx is given by dou u by dou x, and epsilon yy is dou v by dou y, and the shear stress shear strain epsilon xy is given by half into dou u by dou y plus dou v by dou x. Okay, so replacing this E in terms of G, you can get the above equations rearranged in this form. You can write it like this: dou u by dou x is equal to 1 by 2g into 1 minus mu divided by 1 plus nu into real part of z1 minus y imaginary part of z1 prime. So this is after the regrouping the above equation after substitutions. Similarly, you get dou v by dou y, which is equal to 1 by 2g into 1 minus mu divided by 1 plus nu into real part of z1 plus y imaginary part of z1 prime. Now we are interested in getting the displacement field, right? So what happens is, since we have this expression for dou u by dou x, so integrating this expression, you will get the u component. So that is what is given here. So you after integration, this is I mean, it's very simple because we have already defined this integral and differential form of this stress function earlier. So it is very easy to rewrite this expression in terms of u. Now this is an elastic constant which is remaining the same, but after integration becomes a real part of z1 becomes z1 bar, and then minus y imaginary part of z1 because it was z1 prime earlier, but now it becomes z1 plus f function of y. This is an integration constant. Okay. Similarly, the v displacement is given by 1 by 2g into 2 by 1 plus nu imaginary part of z1 bar minus y real part of z1 plus g as a function of x, which is an integration constant, where f of is the constant of integration, which can be a function of y only. Similarly, g of x is a function of x only. For fracture problems, f of y and g of x can be equated to 0 without losing generality. So this is an advantage. Thus, the displacement field can be written in this form. For the crack center as the origin, we have to use this stress function z1 is equal to sigma z divided by square root of z square minus h square. For the tip as an origin, we should use z1 is equal to k1 divided by square root of 2 by z0. So this is very important. So this particular origin, the very near crack tip, this we have already seen in the stress field equation development. So that's not a problem. So there has to be a clear-cut distinction between where you look at the whether it is a stress field or a displacement field, whether you look at the origin as the center of the crack or the crack tip, which is very important. Similarly, for the plane strain, for a mode 1, the stress strain relationship is modified by the elastic constants like this. Then substituting this, the stress components in the above equation will read like this, which is epsilon xx equal to 1 minus mu squared by E into real part of z1 minus y, imaginary part of z1 prime, minus mu by 1 by mu into real part of z1 plus y, imaginary part of z1 prime. For epsilon fyy also, it is a similar expression except this sign change here. These two places, rest all the expression is same, and then you can rearrange this above equation, group them into for the similar terms. Then you can get the epsilon xx, that is dou u x by dou x, which is equal to 1 minus mu square by E into 1 minus mu by 1 minus mu into real part of z1 minus 1 plus mu by 1 minus mu into y, imaginary part of z1 prime. So similar expression is for epsilon yy except this the sign change, right? So these expressions are a bit longer, but then it is very easy to understand and then substitute and then realize this displacement. So integrating once again, replacing E is equal to 2g into 1 plus mu, we get this u is equal to 1 by 2g into 1 minus 2 mu into real part of z1 bar minus y, imaginary part of z1. Similarly, you get to be 1 by 2g into 2 times 1 minus mu into imaginary part of z1 bar minus y, real part of z1. So what is important to note here is this is for the crack tip is referred as the origin here. So this is this function is being used, and we can also now this is for the center as a origin. So we can also write these expressions in terms of r and theta, like we have done in the stress field. So for that, what we need to do is, this is just a summary to just put it as plane stress and plane strain displacement fields for mode 1 and for the two conditions. We will now just try to rewrite them into very near tip displacement field in the polar coordinates. That is, we can write this function in terms of r comma theta. How do we do that? So this expressions we have already known. This is also we know how to write it. All that we require is z1 bar. So how do we get z1 bar? Z1 bar of this expression is nothing but 2 by pi to the power half into k1 times square root of z0. So z0 we can write in terms of r comma theta, like we wrote in the stress field equation. We can write it like this. So you get these two terms. Then now we can write the displacement field also in terms of r comma theta, like this. Okay, for the plane strain, for a plane stress and a plane strain. So what you have to understand from this here is you see that for a plane stress, this you have the three components ux, uy, uz, very important, which is uz is equal to minus into 2 nu by e k1 square root of r by 2 pi into cos theta by 2 into b. B is the model thickness. Okay, so for the plane stress, the displacement is 3. In fact, we have looked at in the earlier basic equation also. When we write the stress tensor for the plane stress and plane strain, we have realized that this is true. Okay. So other point is in the stress field, what we looked at it, at the tip of the crack, we what we have seen that when R turns to 0, that means the stress goes to infinity. That means to have the root R singularity value, right? Similarly, but if you say that R is equal to 0 here, it becomes the total U becomes 0, because the crack means it's a free surface, right? That is Y is equal to 0. So that is also valid here. So we can re-verify that thought process by just putting at R is equal to 0, then the whole displacement is become 0. So that is one important point to keep in mind. So this is a combined form for the displacement field for both plane stress and plane strain, which is given by this constant, which is also given in most of the textbooks like that. The other important point we have to now remember is crack opening displacement. If you recall, in the fracture parameter table, the one of the fracture parameter proposed by Wells, it is especially practiced in the UK. This is called a crack opening displacement. So now we can just try to get an expression for crack opening displacement through this Westergaard stress function. So this Z1 is this, and Z1 bar is integration of this integral. So we need to look at the integral value of this and then try to get the expression for this stress field. So what is that we are just trying to get it here is, this is the so we are trying to get the displacement U here. So the total length is 2U, but we are trying to get the U, where on this line Y is equal to 0, but then we are interested in calculating the COD between minus A to plus A, minus A to plus A. So this opening displacement is still a valid parameter to calculate, because on the x-axis we are on the crack axis we are considering Y is equal to 0, but as a COD we are calculating between minus A to plus A. That is how we have to understand. So this is what it is written here, Z1. This can be recast. We will see how to recast this equation in the next slide. So integration of this equation can be done by some simple substitutions like this. Take m is equal to z square minus a square, and differentiate this. Dm is equal to 2z dz. So now you substitute this z dz here. That means then we can simply integrate this. Then it becomes a very straightforward integral. Then the solution becomes sigma square root of m, where m is equal to z square minus a square, and then we can put it like this. And for y is equal to 0, for any value of x can be this sigma into square root of x square minus a square, and this can be rewritten like this, and take the minus sign outside, then I sigma into square root of a square minus x square. So the one advantage of writing it like this, so we will simply take the imaginary part of Z1 bar, so we can directly substitute this. So that is the advantage of writing it like this. So if you take this and then put it into this equation, what we will get is very interesting result. So this is the displacement U. You are getting this 1 by 2g into 2 sigma by 1 plus nu times the square root of a square minus x square. And COD is 2u, 2 times u. So you get this in terms of this equation, and then you substitute g, replacing g and u by e, then you get COD is equal to 4 sigma by e into square root of a square minus x square. Okay, and then also the maximum COD when x is equal to 0. The COD max is 4 sigma a by e. So the another important point to realize this particular equation can be recast into the equation called ellipse equation, right? X square by x, a square plus y square by b square is equal to 1. So we can recast this equation, which is because this is a y displacement. So that also confirms that the every crack try to opens as an ellipse. So it's an ellipse equation, COD equation gives us an ellipse equation. That is also an evidence that most of the crack they try to open it as ellipse, as we show in all the animation in this particular chapter. Okay, so now we will discuss another important topic in this lecture, that is evenly spaced collinear cracks in an infinite strip. See, we have now looked at stress intensity factor for a central crack, and then we also know how, if we shift the origin to the crack tip, how the stress field equations are derived and displacement fields are derived. Okay. Now I want to look at the other related topic, which is evenly spaced collinear cracks in an infinite strip. So Westergaard has given a very general solution for this kind of geometry, where it is an infinite plate which is subjected to again a biaxial loading. So and then you have the cracks, elliptical cracks. They are placed in a equidistance by W, and then Westergaard has given a stress function something like this: Z1 is equal to sigma sine pi z by W divided by square root of sine square pi z by W minus sine square pi a by W. Okay, so the a by W is the one factor which we have already seen, that when we introduce a by W, then even in the energy release rate was normalized, right? By looking at the different crack length, we just, after introducing the factor a by W, which was as a constant beta, then the G also converged into a single value point. So similarly, when we bring the factor a by W, there are so many problems can be solved. So this particular type of evenly spaced collinear cracks problem is considered as a mother of all solutions. So we will be able to derive so many stress intensity factor from this solution. So that's what I want to introduce. So let us see one by one quickly. So the stress intensity factor given for this kind of problem is similar to K1 sigma root of pi x. So this is already, we know this is already there. So it has to be multiplied by a factor, a tangent. So W by pi a into tan pi a by W to the power half. So this factor has to be added. So now we will try to understand this, why it is being added, which is basically provided by Irwin and Westergaard and Coiter. Okay, so we look at the details one by one. So in the view of symmetry on edges A and CD, no shear stress can exist. Suppose if you consider the a strip like this, which is subjected to uniaxial loading like this. So central crack is the length 2a and the width is W. So on edges AB here and then CD, no shear stress can exist. Further, they have to remain straight. This leads to the development of sigma x stresses on the boundaries. So what is shown here is sigma x is developing along the crack axis. So that depends upon the thickness, the crack length and the width. In fact, that is why the factor a by W comes into the picture. So as long as it all depends upon the A and the W length, the influence of this the stresses which are sigma x developed on the side is going to be decided. So that's why the A by W factor is brought in. So that is very important. So now we look at the crack in a plate of finite dimensions. So far we have looked at the crack problem in an infinite plate subjected to biaxial loading, and then we looked at the origin of the central crack as well as the tip. Central as the origin, as well now crack tip as also origin. We have seen the solutions. Now we look at the finite dimensions. So that means it is a fixed dimensions. Here in a plate of finite dimensions, an edge of plate may be closer to the crack tip. Okay, so the edge, what we are talking about, whether it is close to the edge or not, that is under a question. So that will influence the stresses. That's what we are saying. The edge may have considerable influence on the stress field in the vicinity of the crack tip and also on the stress intensity factor. So that is what it is shown here. So now it is a finite dimension. If the influence of the stress components parallel to the crack face on K1 is ignored, then K1 of collinear cracks in an infinite strip could be approximated as a solution of K1 for the finite strip is in this form. Suppose if you ignore this, the influence of the stress components parallel to the crack face on the K1, then we can use this term, stress intensity factor for a finite dimension can be of this type, that is K1 is equal to sigma into square root of pi a into W by pi a into tan pi a by W to the power half. Finite plate with the central crack, and then the general solution is of the form. So K1 is equal to sigma into square root of pi a into F1 alpha, where alpha is 2a by W. So this is a general solution, can be written like this. And several people have given some solutions. For a finite plate, Pedersen has obtained an expression for stress intensity factor as K1 is equal to sigma into square root of pi a into secant pi a by W to the power half. So this is proposed by Pedersen, and its accuracy is plus or minus 3% for alpha is less than or equal to 0.7, and its accuracy is 1% for alpha is taken as 0.8. So this is another important idea. And Tada has reported the function f1 as f1 is equal to 1 minus 0.25 alpha square plus 0.06 alpha to the power 4 into square root of secant pi a by W. This has got an accuracy less than 0.2% for all alphas. So now we have looked at three expressions for the similar problem. So now we will compare this, how this results appear. So this is a plot of K divided by sigma square root of pi a versus 2a by W. That is influence of 2a by W on the stress intensity factor given by or proposed by these three people, Pedersen, Tada, and Arvind. So you can see that all of them are almost closely agreeing to each other. So the next one is the edge crack in a large plate. That means this is a finite dimension with W as a width, and then initially we looked at the central crack. Now you look at the edge crack with the length A. This half of the total length is 2a, so half of length is a. So the stress intensity factor is given by K1 is equal to 1.12 times sigma into square root of pi a. So what is to be noted here is for the central crack, the stress intensity factor is K is equal to sigma square root of pi a, which is now 1.12 times more than that of the central crack. So that means the severity of the crack to the edge is more as compared to the central crack. Why it is so? This is because the face which is there in this plane, it is a back free surface. So this is a back free surface, and then since it is this end is already open, this is and this edges will subjected to a free opening displacement again. So the stress which is required to open this also becomes higher. Keeping this crack opened also is higher. So that is what it is given as one of the reason. And for a long edge cracks, alpha is equal to A by W, and K1 is sigma into square root of pi A F1, where F1 is given by this numerical relationship by Brown and Stoll. The accuracy of this expression is within plus or minus 0.5% for alpha is less than or equal to 0.6. Okay. So the importance of this kind of expression is to alert that the edge cracks are much more dangerous as compared to the central crack. So that important message you should carry from the slides. And then again you compare these models with proposed by different people. Plot of normalized stress intensity factor versus normalized crack length for a single edge cracked plate, and you will see this variation was like that. Now you can also look at the double edge crack. Earlier we had a single edge crack, now it is a double edge crack. And Bentham and Coiter have given an expression like this. You see that for all the expression, this remains same. That is the beauty of this analysis. The basic equation given by Arvind, this is intact, and then people keep modifying this function, which is basically the A by W, how the A by W is going to get influenced by this multiple cracks. Okay, so that is what it's given here. So F1 is equal to 1 plus 0.122 cos squared into pi alpha by 2 into square root of 2 by pi alpha into tan pi alpha by 2. So this is given by Bentham and Coiter, which has got an accuracy of plus or minus 0.8% for any value of alpha, where alpha is 2A by W. Yeah, this is given by other person. Nishitani is given by other empirical relations, which has got accuracy of plus or minus 0.5% for alpha is less than 0.8. So we can compare the stress intensity factor again as a function of A by W given by the Bentham and Coiter and Nishitani. So they agree very well with each other.